Today we're going to take a look at 1.5. 1.5 and 1.6 are the last two sections we do in chapter 1. So this is the second to last for chapter 1. And we're going to look at transformations, so how you can take a function and shift it, like left and right and up and down, or stretch it. Mostly just stretching up and down today. And we're going to focus on doing that with quadratics. Okay, so everything that we look at is going to be a parabola shape. That's the basic shape we're going to work with. Let's see. Okay, so first of all, what is a quadratic? So a quadratic is an equation that's of the form ax squared plus bx plus c. And the a, the b, and the c are generally numbers, but a can't be 0. What would happen there if you plugged in 0 for a? Yeah, River?
It would just be x squared.
If you plugged in 0 for a, what would happen to x squared?
Oh, yeah, they multiply and cancel out.
Yeah, it would get rid of it, right? If you plug in a 0 right here. So this would be gone. And what kind of equation is that? F of x equals bx plus c. Yeah, that's like slope-intercept form. That's a line. That's not a quadratic. So if you're going to have a quadratic, you have to have something squared. So we can't let a be 0. Okay, so let's graph y equals x squared, just to make sure we remember what that looks like. This is called the parent function. Okay. The parent function is the simplest function you can have in a given category. So that's the simplest parabola that we can do. Y equals x squared. Okay, so let's put that in. Hit graph. And there we go. That's a parabola. Does anybody remember what you call this low point on the parabola?
A minimum.
Yep, it's a minimum. And there's another name for it. That's a term you use in geometry too when you're talking about shapes, like 3D shape or even 2D shapes, yeah?
Vertex.
A vertex, yeah. It's called a vertex. So now what I want to do is instead of x, let's put in negative x. Okay, so in parentheses, we're just changing the x to a negative x. Anytime you have a negative, you always want to put it in parentheses to make sure that you're squaring the negative and the x. Okay, and I want to look at the difference between those two. So I'm going to leave the top one, and I'm going to graph the bottom one with it. What's the difference between those two? Yeah, Jack? Nothing. There is no difference. Now, technically, the negative did do something. You just can't see what it did because of how a parabola looks. The negative caused the graph to reflect. Do you think the parabola just reflected over the x-axis or the y-axis? Yeah.
The y-axis.
Yeah, it did. This negative caused it to flip over the y-axis. But we can't tell that because the y-axis is a line of symmetry. When you reflect something over a line of symmetry, that means the shape looks exactly the same on both sides of it. So when you flip it, you can't even tell you flipped it. Kind of like if I took the letter x and I said flip the letter x over that line, it would look exactly the same because it's a symmetrical shape. So parabola, not the best example to look at something flipping over the y-axis, but that is technically what this negative did. Okay, flipped it over the y-axis. So we mentioned earlier that that lowest point on the graph is called a vertex. Now, when you draw a parabola, does the vertex always have to be at the bottom? Where else could it be?
It can be at the top.
Yeah, it could be at the top if you flip it. Right? So this is a vertex up there too. And yesterday on the graphing calculator, did we do second calc and look at the maximum? We did the rocket problem. We found the maximum height of the rocket. Yeah. So we can find the highest or the lowest point of a parabola using second calc, minimum or maximum. Depends which one we have. Any questions on that? So the rest of today, we're really just going to take a look at this equation and see what happens when we start changing the A, the B, and the C. Okay, what effect does that have on how it looks? So we're just gonna try it. So the first thing I want to look at is what happens when you change A. Okay, before we graph it, does anybody have a guess what changing the number in front of x squared is going to do to the picture? Yeah. So you think it's going to make it like narrower or steeper? Okay, so let's take a look and see if that's what happens. So we've got 1/3 x squared and 2x squared. Okay, there's different ways you can type in 1/3. That's how I do it as a fraction. It's not the only way. I'm going to do zoom 6. Make sure my window is set. Okay, there's your original. Here's the 1/3 x squared in red. And here's the 2x squared in black. So the way that we're going to describe what happened here is either a stretch or a compression. So imagine all these parabolas, they're made out of something like flexible. And they're all glued down right at the origin. Well, if it was glued down at the origin and you pulled up on it, it would start to get tall and skinny. I think what happens if you start to stretch something out. It gets thinner, like as you stretch it, taller. Or the other one, like the red one, that one got wider. So what happened with the red one is imagine you had, again, the red one is like glued down right there, and you start to push down on the sides of it, straight down. If you did that, it would widen out. Just like if you had like a ball of clay and you push down on it, it starts to widen out. So these graphs are either getting stretched taller or compressed. And the bigger or smaller that I make the number, the more I can see it. If I do 6x squared, that's an even bigger number. It stretched it even more vertically and made it skinnier. If I do something like 0.1x squared, there we go. That's even smaller than 1/3. 1/3 is 0.3 repeating. This is 0.1. So because that's an even smaller number than 1/3, it's going to look even wider. Okay, so these are all called vertical stretches or compressions. What do you think the number is that you can put in front that changes it from a stretch to a compression? What do you think the kind of like the division is? If you're bigger than this number, it'll do something. But if you're smaller than this number, it'll do something else. Caleb? 1, yeah. It's all about the number 1. If you plug in a number in front that is bigger than 1, the graph will stretch vertically. It gets really tall and skinny. Bigger the number, taller and skinnier it gets. If you plug in a number between 0 and 1, like 1/3, 1/2, 0.2, anything between 0 and 1, that will cause the graph to compress vertically. And that's when it looks wider, because it was squished down. So that's the effect of changing A. Any question on A? All right. So now I want to do something kind of like we did before. I want to do something with a negative, but this time I want to put it in front of the whole thing. Okay, I'm not putting it inside with the x squared. This would be different. That's kind of what I showed you before. Now I'm putting it in front. Anyone ever guess what a negative in the front is going to do? Yep. Okay, it's going to flip it. Could you describe it in terms of like an axis it's going to flip over?
It's going to reflect over the x-axis.
Yeah, it's going to flip over the x. Okay, whenever you see a negative, a lot of times a negative has to do with making it flip. Especially multiplying. It's like multiplying by -1 in front. So let's do negative x squared. I'm having trouble. Negative x squared. Let's do -1/3 x squared and -2x squared. So what's actually happening here, these are two separate things. The negative does something, and the 1/3 does something. That's going to flip it. That's going to compress it. That's going to flip it. That's going to stretch it. So it's important to understand that these are two separate things, the negative and the 2. Don't think of them together as one thing. Okay, so let's look at our graphs. Okay, there's your original. There's the original flipped. That's been flipped and compressed. And the pink one has been flipped and stretched vertically because it got skinnier, so it's stretched out. All right, so that negative causes reflections over the x-axis. When you describe that, you can either say reflect over the x-axis, you could say flip over the x-axis. You can also call it a vertical reflection. That's the same thing. If you had a shape like that, and it ends up like that, you flipped it up to down. That's a vertical reflection. If you flip left to right, that's a horizontal reflection. Okay, so now we want to take a look at this problem. And it's asking us how we can get that graph starting with that graph. So the first thing I want to make sure we understand is how many things you have to do to this to change it to that. How many things do you have to do? Yep.
One.
More than one. Yep.
Two.
Yeah, there are two things happening to change this into that. What's one thing that you looked at there that's telling you something's happening? Yeah?
That's negative.
The negative, okay, that's doing something. And what's the other thing you looked at?
5.
The 5. The negative and the 5 are each doing something. So now what we'll do is describe what they're each doing. Let's start with the 5. What is the 5 going to cause our graph to do? Caleb? No, the 5 doesn't.
My bad.
Just the 5.
gonna stretch it out.
Yeah, which way is it going to stretch it? Vertically. So the way I'm going to have you guys write that is vertical stretch, and then you have to tell me by how much. Vertical stretch by a factor of 5. Okay, so that's the first thing. And we already said the negative, that's the next thing. And can someone else tell me what the negative is going to do? Yeah, Jack? Let's describe it in terms of an axis. Which axis is it going to reflect over? Yes, that's a vertical reflection. Yep, because you're flipping up to down. That's vertical. So when you flip up to down, that's over the x-axis. Now, in that one, I kind of led you and told you, let's describe what the 5 does first and what the negative does second. In general, the order that you describe them in is important. Okay, so when we start getting into more transformations, I'm going to give you an order that you always have to follow when you list them. And it's kind of like PEMDAS. Okay, it's just the order you have to list them in. Okay, but what we did on that question is correct. Okay, vertical stretch and reflect over the x-axis. Okay, any questions how we got those two transformations? So let's look at something a little different. So let's not mess with the number in front of x squared anymore. Let's just leave the number in front of x squared as a 1. What I want to look at now is adding or subtracting a number on the end of the function. I want to have a guess what that plus 2 is going to do. Works?
Is it the y-intercept?
Yeah, it's going to be, in this case, it'll be the y-intercept. So what's the kind of transformation that's happening?
It would move it 2 blocks up.
Yeah, it's going to shift it 2 units up. And that's exactly what we'll write down. So to get y equals x squared plus 2, we would shift the original y equals x squared up 2. That's what the plus 2 does. And then how about to get this one? How do you think you'd get x squared minus 3 if you had the original and had to do something to it? Julia?
From using from the original to x minus 3, like the x minus 3, you just subtract.
So how would you write that one down?
You're saying that one, right?
Yeah, this one, just like we did the top one.
Put down -5. From x squared plus 2 to x squared minus 3, you go down -5.
So if you're starting with this one,
Oh.
and you're going to get that one.
Okay, so then you go down 3.
Yeah, we just go down 3. Yep. Okay, so the plus 2 and the minus 3, we just shift it up and down. Okay, we can double check it. Let's put in x squared plus 2. There's your original. And there's the plus 2. It's been shifted up 2. No change in the width. Okay, they're exactly the same width. They're just taking what you have and moving it to a different spot. And that's called a rigid motion transformation. Rigid means that you just take what you have and it's like a translation, like from geometry. No stretching at all. So with vertical shifts, there's two cases. You either shift up or you shift down. If the number at the end that I circled right here is bigger than 0, you would shift up. If that number is less than 0, you would shift down. Now, how come I wrote shift down absolute value of k units? Why did I put absolute value? Yeah.
Because distance can't be negative.
Right, you're moving a certain amount of units, so you wouldn't want to say something like shift down -5 units. That doesn't make sense. You can shift up 5, you can shift down 5. But you're always moving a positive number. Okay, down is the negative. Yes?
Wouldn't K also be C?
Wouldn't K also be C? So it depends on how we write it. I'll talk more about that in a little bit. Yeah. So like if you had something like, just look at one like this. This -3 doesn't guarantee it's gonna, I don't know if you were getting at like the y-intercept, it doesn't guarantee it's gonna cross at -3. And in that case, this is not the C value. Right? And I'll show you why that -3 is not C. The C value there would actually be 1. So if you were going to write this all out, the C value in this problem is really 1. So we just have to be careful when we look at the number at the end. But yeah, in this case, yes. This is C in this case. All right. So any question on when you shift up or shift down? All right, so we're going to look at something similar. Okay, we're going to look at adding and subtracting a number again, kind of like we did up above. But this time we're going to add and subtract on the inside of the parentheses, not outside on the end. Does anyone have a guess what that's going to do? Adding or subtracting inside? Yeah.
Shifts left to right.
It's going to shift left or right. Okay. Anytime that you do plus or minus a number, it's always a shift. Where you do it controls if it's up and down or left and right. If it's outside the parentheses, it's up and down. If it's inside, it's left and right. Which way do you think x minus 3 is going to shift it?
Left.
You think it's going to shift it to the left? How many units? 3. I definitely agree it's going to shift 3 units. Let's see if the red one is 3 units to the left. Here's your original. Did the red one move 3 units left? No, it went 3 units right. What about x plus 2? What do you think is going to happen there? Yeah?
2 units to the left.
So you think that's going to go 2 units to the left? Yeah. So that one went 2 units to the left. So it's not quite what you would expect. Right? Minus moves it to the right, plus moves it to the left. So let's write that down. Okay, so to get y equals x minus 3 squared from the original, bless you. Okay, we're going to shift y equals x squared right 3. I always have to think about it. And then to get the other one, y equals x plus 2 squared, you would shift the original left 2. Okay, so this is another rigid motion transformation. It's not stretching it. It's not distorting it. It's just taking your picture and translating it somewhere else. Yeah.
Why is it like opposite?
I'll touch on that in a little bit. I'll talk about why it's opposite. I mean, I guess I can talk about it right now. So let's say you had y equals x squared, and we just pick a couple points we put on the chart. Okay, if we plug in 0, what do you get when you square 0? 0. Let's do 3 points. How about when I plug in 2? What's 2 squared? 4. And if I plug in, let's do one more, 5. What's 5 squared?
25.
25. Okay, so those are just a few points on that parabola. Now let's look at the x plus 2. Okay. And I'm going to pick some similar points. Let's say I pick negative 2. What do you get when you plug in negative 2? You get 0. How about if I plug in 0 for x? I get 4. And what if I plug in 3 for x? I get 25. Okay. Notice these y values are exactly the same. I did that on purpose. Compare how the x value changed to give you the same y value. What happened between this x value and that x value? Minus 2. Now think about a number line. If you minus 2 from the x value, what direction does that move you? To the left. Look at this one. These each have the same y value. This one was a 2, this one was a 0. How do you get from 2 to 0?
Subtract 2.
You subtract 2. That moves you 2 to the left. So if you make a table for corresponding points, you can see to get exactly the same y values, all your x values are 2 units smaller, which moves you to the left. That's why plus 2 moves you left. That kind of makes sense? All right, so let's write this down nicely. So these are horizontal shifts. And there are 2 cases. You have to focus on what I just circled right here. If that number is greater than 0, like it was right here, plus 2, a plus is going to move you to the left. Positive values move you to the left. Greater than 0, left. A negative value is going to move you to the right. And that's like this one. That's a negative 3, and negative moves you to the right. And now that we've talked about moving left and right and up and down, we can identify something like this. I can give you a problem and ask you, where does the vertex end up? Okay, so I'm going to show you the formula for that. To figure out where the vertex ends up, you just have to take into account, did you move left and right, or did you move up and down? Multiplying by a number in front has no effect on the vertex. Okay, that's a vertical stretch. Doesn't affect the vertex at all. H and K are the only 2 things that affect the vertex. But what you have to remember about H is it moves in the opposite direction that you would think. So if you have something written like this, and you want to know the vertex, it's negative H. So take the opposite of that number, comma, K. K, there's nothing tricky about K. Positive is up, negative is down. So that's the formula, that's the coordinate for the vertex. Negative h, comma k. Now, the line of symmetry. What direction is the line of symmetry going for a parabola? All parabolas have a line of symmetry that goes, yeah,
Vertically.
vertically. So if you had a parabola, and you draw the line of symmetry, how does the line of symmetry change if I shift the parabola down? Yeah, it doesn't. How about if I shift the parabola up? How does the line of symmetry change? It doesn't. So shifting up and down has nothing to do with the line of symmetry. So K is not a part of the line of symmetry. The only thing that we need for the line of symmetry is H. And because it's always a vertical line, your equation is x equals negative h. So if you saw a plus 2 inside here, your line of symmetry would be x equals minus 2. It's always the opposite of that number. All right, so let's try this one. And let's find the vertex and the line of symmetry. Let's start with the vertex. If you're not sure, I'll show you another way you can think about it. But since I have the formula on the board, let's try to do it this way. What is the number inside the parentheses with the x? Yeah?
H.
Okay, it represents h, and what is that number in this problem?
Plus 2.
It's a plus 2. Okay, so this is a plus 2. And what about the k? What's k in this problem? Yeah? Negative 3. So now just fill those two numbers in, here and here, and that's your vertex. So what is our vertex going to be? Yep.
Negative 2, negative 3.
Negative 2, negative 3. And the line of symmetry, it's always vertical. And how does the equation of a vertical line always start out on the left side? We talked about that yesterday in 1-4. How does the equation of a vertical line always start? This was a special case, Lewis. Yep, it always starts out x equals. So it's not y equals mx plus b. Okay, it's a special case. X equals. And what would be the number on the other side? Yep. Negative 2. Yeah. So make sure anytime you write the line of symmetry, you write it as an equation. Don't just put negative 2. Okay. Any question on that one? Vertex and line of symmetry. Now, next one we're going to talk about the order that you write the transformations in is going to matter. So at this point, I should tell you the order that you should follow. Now, there are a couple transformations that I did skip there. You'll notice there's no horizontal stretch and there's no horizontal reflection or reflection over the y-axis. Those two transformations would be right here. Horizontal stretch, horizontal reflection. I didn't put them in this list because we don't need to work with them today. Eventually we do. But for today, those are the only ones they cover in this section. But the general pattern is you have to handle all your horizontal transformations first and your vertical transformations last. And there are technically 3 horizontal and 3 vertical. But we're only dealing with 1 horizontal today. So the first thing you look for is a horizontal shift. Then you look for any vertical stretching or compressing. The third thing is any reflections over the x-axis, which is a vertical reflection. And the last is any vertical shifts. Now, I put if necessary after number 3. They're all if necessary. You might have or not have any amount of these in any problem that we do. But at most, you would have 4. And you wouldn't have more than 4 for now. So let's look at this one and see if we can describe the transformations. Now, if you're kind of wondering, why does the order matter? What's the difference? Well, in your head, think of a number, times that by 5, and then add 4 to it. Think about what you get. Now do it the other way. Take that same number, add 4, and then times it by 5. You don't always get the same thing. So when we describe transformations, that's why it has to be in a certain order. Or we don't get the same picture. Okay, so first step, let's identify how many transformations we have. Anyone think they can tell me how many transformations it's going to take to change that into that? Yeah, Luke?
2.
2. Yep, there are 2. And what we'll do is we'll go through our order until we find one, and then we'll write it down. Let's start with horizontal shift. Dylan, is there a horizontal shift in this one? No? No. You sure? Okay, good. Yeah, there's no horizontal shift in this one. So we're going to skip that one, and we're going to go to the next one, which is the vertical stretch. Okay. Is there a vertical stretch in this one? Where's what do you think?
Yeah, there's a vertical stretch, the 5.
Yes. So we're going to write vertical stretch by factor of 5. So vertical stretch by factor of 5. Okay, go to the next one on the list. Reflection over the x-axis. Is there a reflection in the x-axis on this one? No. What would we be looking for if there was a reflection? We would have something in a certain spot. Yeah.
A negative in front of the 5.
You would have a negative in front of the 5, and you don't. So no reflection. Do we have a vertical shift? What do you think, Mia? Where's our vertical shift? Yep. And how is that going to change how the graph looks?
It's going to move it up 4.
Yep. So we're going to say shift up 4. Perfect. Okay. And those are how we describe the transformations. Let's try one more of those. Let's do this one. So they want us to describe again and then find the vertex and line of symmetry. Okay. How many transformations are in this one? Yeah.
3.
Can you tell me what are you looking at that's telling you it's 3?
There's the +4.
Plus 4, that's 1.
The -1, which would move it over.
That's
1.
2.
And then the -3, wouldn't that be?
That's 2 things.
2.
Yeah.
The -3, wouldn't that be its own thing?
Well, that's negative 3, you're saying two things at the same time,
Okay.
right? The negative does something and the 3 does something different. So we're going to separate those two out. Okay. So there are 4. What's going to be the first number that we focus on? Yeah,
-1.
-1. Yep. And what's that going to do?
It's going to move it over 1 to the right.
Yes. So shift right 1. Perfect. What's the second thing we focus on? After the -1.
3.
Yeah, the 3. What's the 3 going to do?
Stretch it.
Which way?
Vertically.
Vertical. So vertical stretch. And just make sure we say how much. By a factor of 3. Okay, so we took care of the 3. Next thing we look at after the 3. What?
Negative.
Negative in front of the 3, and what's that do?
It's gonna flip it over the x-axis.
Yep, flip, reflect, same thing. Reflect over x-axis. And the last thing we're going to focus on is the +4, which does what, Caleb?
Vertical shift of 4.
Yep.
So by factor of 4.
Say that one more time.
Vertical shift by factor of 4.
So factor is only when you're stretching. So this one, how would we say this one?
Just vertical shift by 4.
Just shift up 4.
Oh.
Yeah. So when you say that something's like a factor of it, like if I said, your grade increased by a factor of 2, that means your grade doubled. If you went from like a 50 to 100 or something. Okay, so that's just for multiplying. What else do they want to know? So we did the describe vertex. Well, where does the vertex start if you don't do any kind of shifting? The vertex is always where? Yeah.
0, 0.
It's always 0, 0. Now, think about what we did. We moved every point right 1 and up 4, including the vertex. So if the vertex was at the origin and it went right 1, up 4, where would it be? Yep. 1, 4. The opposite of this number, comma that number. And last thing, line of symmetry. Okay, line of symmetry, because it's a parabola, is going to start out with what letter? Yep, x. And it's going to be x equals, yep, 1. It's the same as this number you used right there. Because it's been moved 1 unit to the right. Yeah.
They could be like questions like this on the test.
Like this?
Yeah.
Yeah.
And then, do you want that in that exact order?
These transformations?
Yeah.
Oh, yeah. Yeah. If they're not in that order, then it would be wrong. Yeah. You got to put them in that order. Now, let's look at this one for a second. This -3 x minus 1 squared, was it +4? I think that's what it was. That's written in a very good way to be able to identify all the transformations. Now, if somebody did this to me, remember, x minus 1 squared means to multiply it by itself. If they decided to FOIL this out, that would actually make things a lot harder. So remember, I told you earlier that this number at the end might not always be C. C is not +4 in this case. Let me show you what C is. It's x squared minus x minus x, that's minus 2x. And minus 1 times minus 1 is plus 1. Now distribute that negative 3 in front. Negative 3x squared plus 6x minus 3 plus 4. What's minus 3 plus 4? Yep. 1. C is 1 in this case. And I can check that I did that right by typing in the original and typing in how I just did it out and see if they look the same. So let's put in negative 3 x minus 1 squared plus 4. And negative 3x squared plus 6x plus 1. Okay, so let's graph them and see how they both look. There's the first one. There's the second one. So how do they compare to each other? They're the same. Okay. This is exactly the same as that. But that is extremely difficult to describe the transformations because we know that we shifted up 4. Well, where's the up 4 here? I see a negative 3, a 6, and a 1. Because somebody took this and they did this all out, that messes up the format we need to find the transformations. It's not wrong, it's the same thing. It's just not easy to tell anything anymore. So the way that we always want it is in standard form. Standard form is when you have a number in front, that's your A, something in parentheses, squared, and then you could have a plus or a minus k at the end. That's called standard form. And all the problems that we do will always be in that standard form. If I gave you a problem that was not in standard form, like this one, you would have to figure out how to change this back to that, which is not something I'm going to talk about right now. But it is doable. But it's extra steps. Okay, any question on that? Okay, so the last one is what is called a zero of a function. A zero is basically a number that you can plug in for x, and when you do the answer out, you get 0. That's what it is. So if I had the equation y equals x plus 4, what number could you plug in for x there and get an answer of 0? Yep.
Negative 4.
Negative 4. So negative 4 is called the 0 of the function. And it is the only 0. Let's draw that and look at what happens at negative 4. Okay, first, does everybody agree that negative 4 is, if you plug it in, you get 0? What happens at negative 4 on the x-axis? Yep.
Y0.
That's where y, yeah, y is 0, and this point has a special name. Yep. The x-intercept. So when you're talking about zeros of a function, it's exactly the same thing as talking about x-intercepts. They're the same thing. Now I want to think about a parabola. When you draw a parabola, how many zeros can it have? Or how many x-intercepts could it have? Yep.
2.
Could have 2. What else could happen? Besides 2.
You could like keep going and have one.
Well, it's a parabola, so it's definitely a U shape. It has to be a U shape. But it could have 2 zeros. Yep.
You could have none.
It could have none, right? You could definitely have a U shape that never crosses. And there's one other thing that could happen. Yep.
You could have 1.
You could have 1. So when we're talking about a quadratic, it can cross the x-axis 0 times, 1 time, or 2 times. And if we don't care about where it crosses, but we only want to know how many times it crosses, okay, or how many zeros it has, there's an easy way to figure that out. And the easy way to figure that out is to do a calculation. The calculation is b squared minus 4ac. And when you do b squared minus 4ac, there's 3 things that can happen. This either comes out to a negative number, comes out to 0, or comes out positive. Does anybody recognize b squared minus 4ac? Yeah.
Quadratic formula.
It's part of the quadratic formula. Specifically, it's the part under the square root. So if the part under the square root comes out less than 0, you will have a graph that never crosses the x-axis. It'll look just like this. Or it could be flipped over and moved down. If the part under the square root came out to exactly 0, you would cross the x-axis 1 time. It's technically not even really crossing it. It's just kind of coming down, touching it, and going back up. And how many times do you think it would cross the x-axis if that came out to a positive result? 2? 2 times. Yeah. Looks something like that. So let's take something like x squared plus 3x plus 2. What's a in this case? 1. What's b? 3. And what's c? 2. B squared is how much? 9 minus 4 times a is 1 times c is 2. What's 9 minus 4 times 1 times 2? That comes out to 1. Is that the top, middle, or bottom case? That's the bottom. B squared minus 4ac came out to a positive number. So if I graph that, x squared plus 3x plus 2, guarantee it's going to cross twice. Where it crosses, I don't know. I didn't do the whole quadratic formula. But I can see that it does cross twice. Might be a little hard for you to see, but I can tell from up here, it definitely crosses twice. Now let's change it to, let's change that to a 4. Just change that one number. What's a this time? Yeah, still 1. How about b? 3. And what about c? 4. So b squared is still 9 minus 4 times a times c. What's 4 times 1 times 4? 16. And I don't even really have to finish it. 9 minus 16 is what kind of number? It's negative, which means this graph would cross the x-axis how many times? 0. That means it has no real numbers that you could plug in to get 0 as an answer. Doesn't mean they're unimaginary, okay, but it means there's no real. So change this 3 to a 4. And let's see if we get a graph that never crosses the axis. There you go. Okay, so any question on that? So that is section 1.5. Okay, so the homework tonight is on page 56. And it's those questions.
Oh, it's
are-
on both pages, it's just 56.
What's that?
Oh, never mind.
Well, they're both page 56. The other assignment?
I thought the top you're talking about.
It's still 56.
Oh.
It's just,
Oh, you just took away a question. Oh, thank God.
okay, so we'll take a look at that tomorrow, and then we'll finish chapter 1 tomorrow as well.